So for today's lab, we're going to go through analysis of variance, and I want to go over some overview just about analysis of variance. So the reason why we learned about analysis of variance is because we're interested in looking at studies with three or more groups, right? So with t-tests, we were able to look at studies, just compare two different groups. But now we're going to look at three different groups. So just a reminder for our null hypothesis is that for three different groups, that the group means will not differ from each other, right? So the mean 1 will be equal to mean 2 will be equal to mean 3. So that's what our null hypothesis is. For the alternative hypothesis, we hypothesize that at least one of the means will be significantly different. So one of the means will be different. And what I want to emphasize here is that it could be any of the means. So mean 1 could be significantly different from 2, but 2 and 3 are equal. Mean 3 can be significantly different from 1, but means 2 and 1 are equal. There's all these different ways that a mean could be different. And when I say at least one of the means, that doesn't mean all of the means are different. It just means that at least one of them is significantly different. And so we learned about post hoc tests because we did not know when you have a significant F value, you don't know if the data or which mean is actually different. You have to do post hoc tests to be able to figure that out. So, and when we run ANOVA, our significance test is using an F ratio. So the F ratio is based on variance instead of sample means. So if you remember with the t-test, we had to compare two different means, so we're able to subtract them. But when you have three means, you can't just subtract them and then figure out, okay, is this mean significantly different from the other, because you have three different means. You can't just simply subtract it. So what we had to use with the F ratio is variance. So variance, so for the F ratio, it's organized in the way where we're looking at between sample means, the variance between sample means as the numerator, and then the variance expected with no treatment effect as the denominator. So what that looks like is our F ratio. The numerator is broken down into systematic treatment effects plus random unsystematic differences. So what random unsystematic differences are just naturally occurring differences that exist in any population. So for example, whenever I give an exam, there's always going to be variation. Not every single student is going to get the same exact score on an exam. Everyone's going to get different scores. So that's sort of how data happens, right? We're always just going to have unsystematic differences. So then the denominator of this statistic, of this F value, will be just random unsystematic effects. So there's two things in this equation that are the same. So when there's no treatment effect, it will be 0. So if there's no systematic treatment effects, it'll be 0. And our random unsystematic differences will be the same as random unsystematic differences. And so when we have no effect, our F ratio will be closer to 1. And so I went over the F ratio, but what goes into the F ratio is looking at variance between treatments, as I mentioned in the previous slide, over variance within treatments. So for variance between treatments, that's our mean squares. Our sum of squares between goes into figuring out the variance between treatments, and so does our degrees of freedom between. And the variance within treatments, or our mean squares within, takes into account sum of squares within and degrees of freedom within. So this is just showing that we have our sum of squares and degrees of freedom go into our variance between treatments, and the variance between treatments and variance within treatments goes into our F ratio. So I want to go over my example I wanted to use is COVID-19 data that I downloaded on August 14th. And what I was interested in, and there's a lot of different things you could look at, but for this purpose, for using ANOVA, I was interested in whether or not there are differences in the type of area or type of setting where it's more likely to have an outbreak of coronavirus. So let me show you what the data. So I have a link to the data. Okay, sorry, I was already practicing before this. So so that link I put on the slides, it goes to this webpage, and at the bottom, we can see, so this is showing Los Angeles County non-residential settings meeting the criteria 3 or more laboratory confirmed COVID-19 cases. So pretty much they have a record, or they're keeping track of different settings. And then if they have 3 or more confirmed staff who are coronavirus, who are COVID-19 positive. So let's see an example here. So, for example, I wish I could find something more like regionally closer to you guys, but there's this CVS in Hawaiian Gardens, and they give the address and has 3 confirmed staff. Let's see. So you guys can go scroll through this and see if there's anything that's close to you guys, I guess, or where you're currently living. But okay, there's this Costco, and there's 19 confirmed staff in Hawthorne. I'm not going to go to that Costco. Okay, so let me show you what that data looks like. So what I did was I copy and pasted the data. So here's setting name, address, total confirmed, so COVID-19 positive staff, and total non-confirmed symptomatic staff. So these are just people who have symptoms, but they don't have a confirmed test. And then I went through, because we have all these setting names, I wanted to go through and I put the type of setting it is, okay? So I put this together, so there could be mistakes, and maybe you disagree with what I decided to put as the setting type. So, but you can look through this. So like, okay, I thought this California Fish Grill goes into food and retail. I have 3 different groups here. So I have workplace, and then I have food and retail clumped into a group. So those are restaurants and Coffee Bean. I put Costco as food and retail. I put any store like that we would be able to like walk in and shop in as food and retail. So food for less. And then there were like a couple of education. So I think we all know that the USC has an outbreak. Let's see if it's on here. Here we go. USC. I don't know why this showed up. But they have 5 confirmed staff. The Housing South complex at USC. So there's only a couple of education because the colleges and schools have been closed. Okay, so then I am using number analytics for this data. I uploaded my data, right? You just press upload. I already uploaded it, so I'm going to press on this and then press open for lab 4. And so here's my data. I just like to make sure that it looks okay. So here's my setting name, setting type, right? So I created this variable for you guys. Address, total confirmed staff, total non-confirmed symptomatic staff. So then I like looking at summary statistics first to make sure, okay, this looks okay. So We have 351 observations. It looks like this is what it's broken down by. So I had 22%, 23% food and retail, 76.1% of my settings were workplace, and then it's like a very small percent of education. It was only like 4, I think, in education. So then I'm gonna go press statistics and then ANOVA test. So again, what I'm interested in is whether or not there's different settings where it's more likely. So like that, like say maybe in one of these settings that there's more total confirmed staff compared to the other settings. So that's my alternative hypothesis, right? So my null hypothesis is that all 3 groups will have the same mean. So regardless, the workplace versus education versus food and retail will have the same total number of confirmed staff. My alternative hypothesis is that one of those setting types will have a higher number of, will have a difference. Actually, it will be a difference in total confirmed staff. Okay? So what I put, so I want to select my data. I want to select my data. And this is the correct data set. Select. And then my dependent variable, again, so I'm interested in the total number of confirmed staff, right? I'm interested in one of these settings have a higher number or different number of total confirmed staff, and then my grouping variable is going to be by setting type, right? Because so setting type is where I determined if the setting was workplace, retail, right? Food and retail, or education. Okay, so I'm going to press run. So make sure that they're both, the correct variables are clicked, right? So I'm going to press run. Okay, so it looks like my F value is 0.465. The P value is 0.629. So I'm expecting, if I wanted a significant effect, my p-value would be less than 0.05, and it's not. So what that means, and you can even see this in this graph, and it shows these variance, variants, I forget what these are called, but you can see that the means between my groups, so I have education, food and retail, and workplace, the setting type, they don't differ between each other. They don't significantly differ. That's what this F value is telling us. So you can look at the means, and even though they're different, they aren't significantly different from each other. So if we did have a significant F value, what I would do then is go to advance, and it will show, okay, so then we want to look at this too, but I would look at, okay, look at the means, look at the standard error, look at standard deviation. Already, the standard deviation and standard error, it's much larger for food and retail, but and for a workplace, but it's very small for education. And I think it's because I had so few in education. See, I have only 4 in education, 80 in food and retail, and 267 observations or N for each of these groups. So these groups aren't balanced, right? Within ANOVA, we want to try to get our groups to be similar. This is like very not great. But this is still interesting, right? This is the data that I could get for COVID. So now I'm looking at, so remember our F statistic? Our mean square is the variation. So this is the variation between groups and the variation within groups. So we can see already like this variation between groups where our mean squared is very small compared to our within groups. So because those two numbers go into the calculation of our F value, we can see that there's almost almost no variation between the groups. We also have our degrees of freedom between, degrees of freedom within, and then our sum of squares between, sum of squares within, and then our total sum of squares and total degrees of freedom. Um, then, so I think there's nothing in here, but this just shows the plot. So with so the problem with this program, we can't do post hoc tests. And we wouldn't anyways because the F value is non-significant. But for your output, please, so copy this. So I'm going to copy it. I actually already copied it, but let me just and paste it. Oops. So, okay. So I want you to copy this sum of squares, and then I also want you to copy these descriptives. Oh, okay. Square. And that should be enough. And then let's go over the write up. Okay, so I want to write up similar to this. So I want you to just say that so we can't do post hoc tests. So we didn't do any post hoc tests, so you don't have to do this. So you just need to write the means and standard deviations are presented in Table 1 and show Table 1. The analysis of variance indicates that there are significant differences among the three. We have to say the analysis of variance indicates there are no significant differences among the three setting types. And then report out the F value. This is theta squared, I believe. That's the effect size. Just report out this F statistic.